welcome back to Introduction to Computer Networks at NTU. And this is the episode 22. Just like all the Wednesday sessions, we'll go ahead and start with the topics. And hi, good morning, Calvin and everyone. And James, right on time. So we need to leave early because IPv4 address format is a little bit complex yesterday. Okay, so we'll continue to talk about IPv4 address. So this video is a little bit long, almost 8 minutes, but it's quite straightforward. Polly will spend some time explaining that each IP address is associated with the network interface, such as a Ethernet card, such as a Wi-Fi card. Okay, so it's not quite to identify one machine uniquely, because nowadays each machine has multiple network interfaces. Okay, and in the second part of the video, you will start seeing that the IP address is 32 bits long. There's a part of it we call the host part, and then another part, there's a part of it we call the subnet part, and the remaining bits the host part. So the subnet part is unique to identify which subnet the network interface belongs to. The host part then is to identify uniquely which network interface it is in the subnet. Okay, so 7.5 minutes. Guys, pay attention, because towards the end of the video, I will teach you how to write the subnet address, and we'll exercise it with the quiz 35.
IPv4 addressing. Well, it's actually quite simple because you guys all know, right? The IP address is 32 bits long, like this. And the way we represent an IP address is more. Take 8 bits at a time, convert it from the binary form to the decimal form. And separate these 4 numbers by 3 dots. So, an IP address. And we actually say that, hey, each machine here is assigned an IP address. Yeah, it looks like it's indeed the case. Okay, but no, that's not quite precise. An IP address is actually associated with an interface. So each network interface requires an IP address. The tricky part is just this. Okay, a host here, okay, being at the end of the internet, at the edge of the internet, there's usually just one connectivity. Therefore, there's only one interface. Therefore, there's only one IP address. If you look here, routers being inside the core of the internet usually have multiple connections to the rest of the internet, therefore multiple interfaces. And you see here, a router can be assigned multiple IP addresses. All right? So routers typically have multiple interfaces, while hosts typically one. Nowadays, we do have 2. Okay, that's why. The reason for that is because sometimes if we do have wire network access, then we can plug into Ethernet, for example, conveniently. In case now, we can still use Wi-Fi. Okay? So regular hosts, we do have 2 physical interface cards, but we use it one at a time. Okay? So this is an end systems characteristic. Now the core systems router, definitely multiple interfaces. And you see a little bit more clearly that the interface is the part that connects a host, okay, to a link like this, to a link like this. Okay. So bottom line, IP addresses are associated with interfaces, not a physical machine. Now, yeah, we did not print any of the links here, right? We did not show any of the links there. Okay, so how these interfaces are interconnected? Through the links, and we'll talk about the links in chapter 6 and 7. So this is the wired link, and this is the wireless link, like this. Okay, this is the wired link, and a link layer protocol called the Ethernet. This one here is a wireless link, and it's the Wi-Fi protocol. Something else about the IP address you should have a rough sense about is this. You might have seen that the machines nearby, okay, the IP addresses for their network interfaces might look alike, especially the first, few numbers. So 223.1.1 seem to be shared by these interfaces that are physically connected. Yes, those interfaces that are physically connected to each other belongs to a subnet. So the first few numbers there, okay, is called the subnet part of the IP address. And the last, okay, that are unique, so we could separate the different different interfaces, is the host part. Those are the bits to the right, okay, the lower order bits. Now, only the interfaces that are physically connected then they will share the same subnet address. Okay. So this is subnet 223.1.1. This is subnet 223.1.2, and this is 1.3. So each of them is a subnet, but these two are not in the same subnet because there's a router intervening. Now, we also use something like this to say, yeah, this is the subnet address. So subnet address. So you see here, this number is to indicate how long the subnet part of the IP address is. So 8 bits, 8 bits, 8 bits, 24 bits. Similarly, then the 223.1.2 subnet address is looking like this. And this is 1.3's subnet address. And what I'm teaching you here is there's an easier way to tell how many subnets we have here. Okay? Because if you want to assign the subnet address, if you need to decide how long the subnet part of the IP address is, you do want to know, right, inside your network, how many subnets there are, and inside each subnet, how many machines there are, or how many network interfaces there are. To determine the number of subnets you have, you need to detach each interface from its host or router. Okay. As a result, it's going to create an island of these isolated networks. So let's detach host, 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 router, host, 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 host. So we get what? One island of these network interface cards, one island of these network interface cards, and another island of the network interface cards. So each isolated island is a subnet. So if you want to figure out how many subnet there is for this network, break all these hosts and routers. Okay. So interface physically connected, we have one up there. So subnet 223.1.1. We do have another one here, these three, and another one here, these three. And guess what? Another one here, right? These two together form an isolated island. Another here, and another here. So we together have 6 subnets here in this network. Until now, all these subnet addresses, we see this part being 24. But this is not quite true. Okay, to be more formal, the subnet part of the IP address can be arbitrary lengths. So the general format is looking more like this. Okay, the IP address on the left, and then an X, a number on the right. This indicates the number of bits in the subnet part. So in this example here, we do have the subnet part being 23 bits long. Say the blue part, only 23 of them. Therefore, the host part, we get 9 bits. So we could accommodate up to these many individual hosts. We could allocate these many individual IP addresses to these hosts. Now, if you have a subnet, that has a number of machines, higher than this, you will need more bits. So this guy here might need to turn black, and we need to use a length of, for example, 22. Now, one last thing to talk about is this. How do we write the ABCD out? So this is how it works. Take the IP address in the subnet, and then convert them to binary form. Write it out. And then cut that IP address right at the part that's separating the subnet and the host part. So essentially, cut there right after the 23rd bit. Turn all the host part of the IP address into 0. And then convert this octet back to the decimal, this octet back to the decimal, the whole octet back to the decimal, and then the whole octet back to the decimal. So if you have an X here, smaller than 24, then this last number here is always going to be 0, right? Because it's always cut earlier here. All these bits will be 0. Therefore, this is 0. Now, as to whether this is going to be 0, well, it depends on, the subnet part. It could happen that all these, the subnet part is also 0, then you have 0. Otherwise, you're just resetting only the host part to 0 in order to write the A, B, C, D out. And that takes us to an exercise.
All right, so that's quiz 35. Good, so as you can see here, you see 36 already, but it's okay. 36 is a little bit open-ended. We need to talk about it anyway. So this is 35. That's exercise writing the subnet address in the CIDR format, or aka the ABCD/X format. So this is the example we saw in the video. So you're asked to do this. Can you write this subnet address out in the ABCDX format here? Okay, so let's go to the score space, channel W12, quiz 35. Guys, you have only 2 minutes. Okay, let's start counting time. All right, guys. Yeah, you guys probably don't need the full 2 minutes. Yes, you are correct. And Anthony, you're the first. You are the winner of the bonus today. Yeah, it is 223.76 and 160/27 because the first 27 bits are all the subnet part because they are in the orange color, right? Good. Yeah, straightforward. And I see that all the teams following Anthony are all correct. Good. So that's how you write the subnet address, okay, given a set of machines network interfaces on a subnet. Good. I suppose that this will be straightforward, and we move on then to the next topic. We now know the IP address format. And the first thing next is provided a machine, how we assign IP address to that machine. Provided a network interface, how we assign an IP to that network interface. There are 2 ways. So in this video, you will see that the dynamic assignment one is called the DHCP protocol. And you will see roughly how it works. All right?
Let's talk about how a host gets an IP address. There are 2 ways, especially in the older time. You have to talk to the system admin first. System admin is going to give you the IP address. And then you manually type up the IP address at the specific place in an operating system. Now, how you do that can change from operating system to operating system. Where you do it exactly could also vary within the operating system from version to version. And some of you might need to reboot, okay, the machine as well in order to have the IP address taking effect. So this process here, the manual approach, very tedious, out of fashion. More fashionable today is to run DHCP, the dynamic host configuration protocol. What it does is to get the host and IP address automatically and configure it automatically. The service is entirely plug and play, so there's no manual effort required. Really nice. And we're using it every day. This DHCP protocol is already part of the protocol stack and part of the operating system. Part of all the operating systems these days, including the mobile phone operating system. So formally, let me introduce DHCP. It allows us to acquire IP addresses dynamically. So what happened there is that our side of DHCP is running the client process. The subnet you'll be joining. The server process is running on the subnet, running on one machine on the subnet. So the 2 sides, client server, will negotiate and reach an agreement. So that agreement is actually a lease on a specific IP address. And that's why my host here gets to use a specific IP address. So with this, we bypass needing to communicate with the system admin, a real person. And the assignment is also automatically done because it's all part of the operating system. But essentially, okay, after the negotiation, we get to use an IP address. But as you see here, it's a lease, meaning the IP address is also temporarily allocated. So that is why it's called the dynamic host configuration process. It only runs for a while. If you leave the subnet, this IP address will be reclaimed by the server. But don't worry, as long as you stay in the subnet, stay connected, stay on, then you get to reuse the IP address. Okay? And this is done by exchanging messages again between the client and server. So there are some more messages being exchanged and periodically so that we could renew the initial lease. Okay, so that is generally how the DHCP works. You see, this is really, really nice for us living now a very mobile lifestyle. And the process is very simple. This negotiation process is very simple. A very simple 4-way message exchange. Okay? And an even simpler version is just 2-way exchange. Okay? So these 2 first messages, they can be actually bypassed. If the user is coming in and out really fast, typically the OS on a smartphone implements more this version of DHCP. Now, let's take a look at the scenario and go through these 4 messages in a bit more detail. So here it is. We've used this network already earlier to explain, right, what's IP address format and what is the subnet address. So let's assume we set up a DHCP server here connecting to 223.1.2 subnet. And we carrying a laptop, okay, running an operating system with the client process already running. So the arriving client process here. Server process here.
All right, so that's how you get an IP address assigned dynamically. So you get a rough sense. Next video tells the exact exchange of the messages. And towards the end of the video, pay attention. DHCP assigns an IP address to a new network interface, all right? It assigns also several other pieces of information. Okay, pay attention to that second half of video because Polly has already asked the pop-up question number 1 today. DHCP assigns an IP address to a new network interface. What else does DHCP assigns?
The first message, DHCP discovery. What it does is the client asking, in a broadcast way, is any of you guys the DHCP server? So if we look into the packet, you should see the source looking like this, a null IP address. And the DHCP client is default on port 68. The server, on the other hand, on port 67. Destination will be going to the DHCP server. But hey, the client doesn't know if there is a DHCP server in the first place, not to mention the exact IP address. So we're sending it to here, the broadcast IP address. A message carrying such an IP address is going to be received by all hosts on the subnet. Therefore, DHCP server being one of the hosts on the subnet will definitely receive the discover message. Why IP address here? Yeah, this is the field to store. The IP address potentially will be assigned to the client. Now, the client has no clue, therefore, it's null. Last is the transaction ID. Now, this is actually quite critical. Usually, it looks like a random number. Okay? Different clients will actually send discover messages carrying different transaction ID. Now, these IDs are also to tell the arriving clients apart. So there could be other clients arriving as well. And they could be sending these DHCP discover messages about the same time. Servers sending responses, DHCP offers, about the same time. How does this guy know which offer is for this guy, and how does this other guy knows, right, which offer is for him? So transaction ID, typically different, coming from different clients, to enable the clients to tell whether the reply is coming for the host or not. So very important. And to respond to the discover message, the server sends the offer message. So this is saying, I'm here. And here's an IP address you could use. And inside the offer message, you see the source being the server's IP address. Destination, again, the broadcast address, because arriving client doesn't have an IP yet, but will still receive a message going to the broadcast IP address because everyone on the subnet will receive such a message. And we see here, the server is offering this IP address to the client. Transaction ID, yep, the same pair. Okay, so this offer is for this discover message. And you see, server here, while offering a specific IP, is also saying, hey, client, you get to use this IP address for 3600 seconds long. Okay, so it's the duration of the lease. Client then say, yeah, DHCP request, okay, I'm going to take the IP address, and this is the content, asking for this IP address. And it's a new transaction for this long. In return, the server sends back ACK, okay, which is simply saying, okay, you got it. Okay, therefore, you see, you got the IP address for this long. And this, again, corresponds to this, okay, not to be confused with other clients requesting for other IP addresses. So this is the exchange of the four-way messages, okay, in DHCP service. Now, in the exchange, DHCP server actually say more, okay, not just the IP address, but a whole bunch of other things that are very critical setting up, okay, the subnet on the hosts. So first is who the first hop router is, because the host message is going out onto the subnet. The default next hop is always the first hop router, because the first hop router then, after picking up, then can determine where else to forward it further. Another important information, DNS servers. This is very critical, right? Because you are requesting www.google.com or www.something, okay, by the name of the server. Okay. In order to know the IP address, you also need to configure on your host the DNS servers. Okay. I know some of you might have some DNS server IPs assigned already, configured already, but if you connect to DHCP server is going to also, okay, add some IP addresses into that part of the operating system. Okay, so the name and the IP addresses of some DNS servers by default. And then the network mask. So this is to tell the host how long is the subnet part of the IP address. So provided the IP address, the DHCP server is also saying that, hey, what is the subnet part? And therefore, okay, the client also know what is the host part.
All right, now you guys know, right, what DHCP server tells in addition to the IP address. So I think James was the one that answered the additional information provided by DHCP server fully incorrectly. Okay, subnet mask. Default gateway is the first hop router. That's another way of calling the first hop router, default gateway. And then the IP address and name of the DNS server. All right. So Anthony is also correct. Calvin, you are right. DNS server definitely is something that DHCP server assigns also to the new network interface. Okay. But on top of IP address and DNS server, there are a couple more pieces of information. Very good. Stanley, Sam, and Louise. Very good. So DHCP is essentially the protocol to dynamically bootstrap a new network interface to a subnet. Okay, very important. You kind of use it almost every day, and maybe every hour, depending on how frequent your DHCP server renew the lease of the IP address. You see that the IP address you're assigned, it comes with the time. After that time, it's timed out. That IP address could be given to somebody else in case you did not ask for it again. All right. So that assignment is dynamic in a way that there's a certain amount of time associated with it. If your network interface, if your machine doesn't renew, then it gets freed and assigned to other people, okay, or other network interfaces. So the third video here is to kind of give you a demo, get a clear sense of how the DHCP's messages go from higher layers down to the network layer and up. Because DHCP's messages are actually sent through UDP. It's kind of routing, it's kind of network layer service, but the messages are sent using the transport layer. It's a application level message. All right. And towards the end of the video, you will also see, what did I want to say? You will also see the details of the DHCP request message and the DHCP reply message. All right, so it can look quite complicated, but you can identify these informations we just talked about. Not only the IP address assigned, but the default gateway IP address, DNS server, name and IP, and the subnet mask from the particular DHCP reply, right? Those information comes back with the DHCP reply to the new network interface.
And to illustrate, you see in this DHCP example, host is right here, okay, we just joined. And DHCP server is already up, and it happens to be running on the first hop router. So what happened there is, the connecting laptop is going to send a DHCP request message out to the network. So this is the simplified version of DHCP. Sending request and server sending ACK. So the laptop here is asking for its IP address. In addition to that, first hop router, DHCP server, and net mask. So DHCP is actually right here, an application layer protocol. And that DHCP discover or DHCP request message is going to be what? Passed to the UDP and adding the UDP header, push down to the network layer and adding the IP header, and push down to the Ethernet and adding the Ethernet header and trailer. So DHCP request gets encapsulated into an UDP packet, further into an IP packet, further into an Ethernet frame. So DHCP is actually implemented at the application layer. Just like DNS, seemingly a lower level functionality, a general functionality, for everyone on the internet, but implemented at the application layer. Complexity at the edge. And it's using UDP as the underlying transport layer service. Now this frame, carrying destination address being broadcast 255.255 all the way, is going to reach all the hosts on the subnet. So this is the entire subnet. By the way, this is an Ethernet switch. It's a rectangle, not quite a circle, so this is not the router. So this is actually the link. So this interface and this interface are connected through this link. So every host on the subnet is going to receive the DHCP discover message. So therefore, the server here is going to pick it up. So this is what going to be extracted, and passed up to the IP layer. This extracted, pass up to the UDP, and this extracted, and eventually reaching the application layer. So the server then can see, this is a request message, therefore send back a reply. So you see here, going all the way, Ethernet gets demuxed to IP, to UDP, and finally, server side of DHCP. Now the server then will generate the ACK message containing the IP address of the first hop and the IP addresses of the DNS servers, and so on and so forth. So process is very similar, encapsulate to UDP, encapsulate to IP, Ethernet, and destination address being broadcasted. The host here, although not having a specific IP address, is going to pick it up. So client now knows the IP address of itself, name and IP address of the DNS server, and the first hop, as well as what? The network mask. So what I'm showing here is the result of sniffing DHCP messages. This is a DHCP request message, and this is a reply of that. Earlier we actually called it the ACK packet, ACK message. And I can use tools like Wireshark or TCP dump to sniff packets travel the internet. Now after sniffing, you're gonna see the content inside the packet. So what I'm showing here is, this is the request message. So you see boot request. And in the reply, or in the ACK message, you see it says boot reply. And you see transaction ID, transaction ID, and they're identical. So this ACK here is for this request. And then you see also specifically the client not having an IP address, but it still have a MAC address. So that MAC address is actually hard-coded into the network interface card that came with your machine. So that is already existing. And that is something that the DHCP client is going to send to the server. So server can identify you somewhat by the MAC address. And then, this is DHCP request, and this is DHCP ACK. And the client is asking for these, right? So the IP address, so IP address is not clear yet. So requesting, this IP address. So this is not a sure thing. It's just that the client suggesting, can I get this IP address? And it's also asking for domain name servers, and the subnet mask. Server here Yeah, in the response, you will see, okay, hey, client, okay, it's okay to use this IP address. Go ahead. In the meantime, it's returning also the subnet mask, yeah, the first hop router, as well as the IP addresses of the DNS servers and the domain name. So all these information, client can then set everything up and then begin to access the internet.
All right. That takes us to quiz 36, and this one is a little bit open-ended. Let me go to the whiteboard mode. All right, so 36. Okay. I don't know if you guys have tried to use one of these free Wi-Fi services around the city. Okay, so Taipei free. It is free, but you often hear complaints saying it's useless. Okay, so here's a news. Okay, reporting the usage of Taipei free, and let me translate that for you. Okay, so what the report says is roughly this. There are quite a few free Wi-Fi access points around Taiwan, provided as friendly gesture to travelers. But you see, 40% of users are not very happy with the free Taipei service. Okay, and among these customers not that happy with the free Wi-Fi service, the mass majority complain this. They can't even connect to Taipei free at all. Okay. And of course, there are other complaints such as, oh, speed is slow, signal is weak, lack of AP spots. Okay, so, but you see, these complaints are more that they are able to connect, but just that after connecting, the speed is slow, signal is weak, very lossy. But mass majority says, hey, I can't even connect at all. So guys, Polly asks you here for Q1. Tell me, what could be causing the trouble? How come some of them, well, mass majority of them complain that they cannot connect? And Q2, how would you address this problem? All right, so according to what you think the cause is, propose a solution. Good. Now let's go to the score space, channel W12, quiz 36. And this one, you guys can see it's a little bit open-ended, and it's definitely related to DHCP and maybe networking, the network layer in general. So let me allow you more time for quiz 36. How about 5 minutes? Let's start counting time. Guys, 1 minute remaining. Okay, speed up. It's very interesting. The score shows how busy you guys are typing up. Ah, there. Thirty seconds. Yeah, time's up. Yeah, good. I think you guys are thinking also all the right direction. So team 6 is first. Esther said that users can connect mainly because access points are crowded by users coming in and out. And they hit the IP address limit provided by the DHCP server. Because for each IP address, the DHCP server allows the user to use it for some time, at least, right? And even though the user might have left the station, for example, a user is entering a station and tries to connect to Taipei Free and get assigned an IP. And then the next second, the train arrived and the user left. But you see that the lease is still valid. And it's going to be valid for some time. So that IP address will be assigned to the user that has already been gone and not assignable to another user. So you see that in a busy intersection, it's very easy that the DHCP server runs out of IP address to assign. And that's well said by Louise. It's the DHCP is an exhaustion problem. Yeah, the DHCP server runs out of IP address to assign, just like when you go to a restaurant, all the seats are taken. All right, so this is one of the main reasons that 74% of users complain. 74% of users complain they couldn't even connect. And of course, ways to address the issue is to, of course, enlarge the address pool. Or shortening the lease time. How about that? Very good. Yeah. So expanding the IP address pool is just like, you know, having multiple access points and each access point assign different address pool. Then the total address pool will be larger for that area. Okay. Good. And I think some of the teams also come up with other reasons that the users don't get connected. It could be that the bandwidth is exhausted as well, right? One might connect, but if there's no bandwidth remaining, then to the user it would appear that it never really connect because you know, none of the messages goes out and none of the replies come back. Okay, so the access points could be too busy. And Yeah, so when the access point is too busy, connection will have trouble running reliably, and it would appear that the user is not connected at all. And sometimes, of course, the signal is too weak for the initial DHCP discovery message to go out and arrives at the DHCP server in the first place. Yeah, so scars or signal strengths of these Wi-Fi access points can also be a reason that the users don't get connected at all. Okay, so you see that the problem here is classified as an open-ended because there's no strict one reason. There are multiple reasons. And the solutions tend to be that you enlarge the IP address pool. You strengthen the deployment of the AP access points, either by enhancing the signal strengths or enhancing the AP density. But you want to be careful about increasing the density because these access points might interfere with each other in the meantime. That might not be a good thing at all because signal interferences could be another reason that the users don't get to connect. All right, so very good discussion here, and let's move on to the next topic. Okay, it's called hierarchical routing. So it sounds like Polly is going to talk about routing, but this is chapter 4. Routing is a subject that we talk about in chapter 5. But in order to talk about other benefits of doing prefix matching, so you see that in an IP address, there's the subnet part, and then there's the host part. The subnet part are the first few bits, right? The host part are the last bits. So it's, again, the prefix of the IP address. You see that in a way, each interface is like human beings, right? We have the last name. And last name is the thing that allowing us to identify which family we belong to. And the first name then is to uniquely identify members of a family. So you see that there's a certain hierarchy there in the addressing scheme. And that works really well with hierarchical routing in a way that we could reduce the amount of messages or route advertisements we need to send with such a hierarchical addressing scheme. So in the coming 3 videos, you will see other benefits of doing the address this way, doing prefix assignment this way. Okay. First video is to tell that, hey, DHCP is the scheme allowing us to get an IP address dynamically from a organization, from a DHCP server. Now the question next is, how does a DHCP server get a group of IP address?
So that was how a host gets an IP address. We ask the system admin for one or a DHCP server for one, which is configured by the system admin. So the bottom line is, how does the system admin get a block of IP addresses so that the system admin can assign to individual hosts? So the next question we're asking is exactly that. Yeah, how a subnet gets the subnet part of the IP address? The answer is quite straightforward. As we ask the system admin for one, system admin asks the higher level system admin for a block of IP addresses. So if we are customers of an ISP, we ask the ISP for the address block. So what I'm showing here is an example. ISP owning a big block of IP addresses. Okay, so by big block, this is how big a block is. Now the prefix of the subnet address of the ISP is only 20 bits, so only up to here. Therefore, that allows us a bigger free IP address space. Now, if there are 8 customers, okay, subscribing from the ISP, organization 0 all the way to 7, ISP can further divide the bigger address space this way, extending the prefix by 3 bits. So that is pushing it further, okay, here. So 3 more bits being included into the subnet ID. Because there are 3 bits, so we could uniquely separate the 8 different organizations. But as a result, we get what? Less free IP space. Each now gets only this much. That is what? 1/8 of the original space. So we are splitting the IP address to 8 equal ways. And it is done very easy by just simply saying this, extending from 20 to 23. Let's say if organization 7 here having 4 departments and each asks for equal share, then very straightforward, right? Extend from 23 to 25, the prefix lengths. And so we'll be actually doing, something like this. Take 2 more bits here, and there are 2 bits, therefore we could identify 4 departments uniquely. And the IP address space is now down to 2 to the power of 7, okay? 1/4 of the second level organization here. So you see, using the prefix there, by sliding it to the right, we actually create also a natural hierarchy in the IP address space and dividing the IP address space. Just like how human beings divide and organize bigger society to smaller society and even smaller society. So this type of addressing, the IP addressing, is also called the hierarchical addressing. Okay. There's actually one more benefit of it, not just that dividing the address space is made very easy, but also this. We could do very efficient route advertisements. Now, routing is one of the major functionality in the network layer. We have not yet talked about it, so in order to explain how efficient this is, let me just give you a slight overview of routing.
All right. So, hey, a really nice addressing scheme with that hierarchy built in, right? So you see, earlier last week, we talked about forwarding. So with the prefix and the host part together, it's easier, right, to forward. It's faster to forward. And the size of the forwarding table can be as compact as possible. Those are the 2 benefits of doing hierarchical addressing. In the video you just saw, it's also easy to distribute the IP addresses from the higher organization to the sub-organizations to the sub-sub-organizations. And you see also towards the end of the video that there's another benefit, that's the 4th benefit. So we can aggregate the routing messages so that the amount of control traffic we need to send to enable internet routing is also reduced. And you know what? We'll explain how. By introducing the very basic internet routing mechanism, the strawman internet routing mechanism in the next video. But before we do that, we'll take a break. It's now 11:08. Let me address a question from Sam. That's when we were talking about DHCP, and then we take a break. Okay, so Sam was asking, will the hard-coded address be repeated by other machines? Okay, that's a very good question. And it happens every now and then. You see that it's related to how a network interface gets an IP address. There are 2 ways. One is fixed, that is done by manual configuration. The other is by interacting with the DHCP server to dynamically get one from DHCP server. So you see that those machines that, or users who know well whether the subnet they would join comes with DHCP server matters. If you know that there's DHCP server already, then all you need to do is just connect to this Wi-Fi subnet or to this Ethernet subnet. Then everything else will be set. In that case, there's not going to be address conflicts because the DHCP server will overlook all the IP addresses assigned. But in case there are users coming with network interfaces that is already manually configured, I think that's what you meant saying by the hard-coded address, right? So in case someone comes into a subnet with DHCP server, but the IP address is already manually configured, then several situations could happen. And it really depends on the operating system this user is running, as well as the DHCP server, how the mechanism there is running. So some DHCP server allows manual IP address configuration as well. So that server can be powerful, discovering that, hey, a certain IP address is already manually claimed. So some IP address, some DHCP server implementation is actually intelligent like this. But most DHCP server implementation assumes that all the network interfaces will get an IP address from it. Okay, and so in case someone comes in with the manual IP address assignment, that network interface might not work. Okay, that network interface might not work. And some operating system will be also strict and claiming that you have a IP address conflict popping up an error message. Okay, so I guess you guys will need to try different combinations of operating systems and the DHCP server implementations to find out exactly what's going to happen. All right. So your question, will the hard-coded address be repeated by other machines? It depends. It depends on the DHCP server running on the subnet. It depends on the operating system running on other machines or the machine coming in with the hard-coded address. Good. And perfect timing to take a break. It's now 11:12. Let's resume the lecture 11:22. All right, let's come back to the lecture. So, coming up, the video explaining a little bit how internet routing works. Okay, and then you will see that the hierarchical addressing helps routing.
The goal of routing is to form these forwarding tables, if you recall, right? Destination IP and outgoing interface. Now, the way these entries are formed is this. If this is a destination, if somebody else on the internet wants to send data to this guy will need to announce its IP address, okay, in an advertisement and travel through the network like this to outside. Okay? That is how the router here discovered, oh, okay, I see a destination potentially this way. So that IP here, and yeah, the outgoing interface is this guy here. Now for a guy, okay, who's connected to the internet this way, that advertisement will go down, yeah, this other interface. So this other guy here, IP prime, yeah, the output interface will be linked here. So that is the general idea of routing. But then you see, for each machine here having an IP address, in order to allow other people sending packets to it, they would each need to send an advertisement announcing its IP address. Okay? And there are these many different IP addresses possible, so potentially worst case, right? Lots of advertisements each of these organizations need to send and travel on these links. And you know what? The most scary thing is this. All these need to go out to the internet, so the ISP needs to send these many advertisements. And that is just not going to scale. Okay, that will be a lot of bandwidth consumption just to send the advertisements. The solution is actually related to the forwarding mechanism in the router. If you recall, instead of listing individual destination IP here, rather we do this individual prefix, okay, and then outgoing interface. So when a packet arrives, the destination IP address matching the prefix, then we send it out on the outgoing interface. You know what? Isn't this a prefix? Isn't this a prefix? So what we're doing, in fact, in the internet is not to send individual IP address in the advertisement. We send an individual prefix in the advertisement. So what's happening there is a prefix in the advertisement gets here. Router here, receiving it, pass it down further. Router here, receiving it, pass it down further, but also add the entry prefix here. And because it's coming this way, so this OIF is going to point to this interface. So when a packet arrives here, matching the prefix, go on this interface, and coming here, this router is going to forward it similarly down this way. And then coming into the organization 0. So by announcing or advertising the prefix, okay, we also draw the data into the organization. And the data is actually destined for one of the hosts in the subnet anyway. So the routers inside the subnet there, we just, we'll be doing further routing there to get to the final destination. Nice. So you see, instead, organization 0, 1, 2, all the way to 7 will be sending one advertisements only instead of these many advertisements. What's even nicer is this, the ISP. Yeah, ISP doesn't need to send 8 individual advertisements out, just send one. Because it's very easy to aggregate all these, right? Because this is the coarser granularity covering, right? Superset of all these subnets prefix. So there's just one advertisement out this way. One on the link, one on this link, one on this link. Advertisements, the distribution of it, very, very efficient. And so here, the entry is simply 200 something something 6.0, and it goes on this interface. Data matching this will all fit and then go on here. This router here then will split the packet 8 ways, and by checking the destination address of the packet to these 8 different prefixes and see which prefix matched better. So that is the idea, and why we say more bandwidth here. This is the third benefit of doing the prefix matching, in addition to what? Making the forwarding table smaller and the lookup process faster.
All right, so internet routing and an additional benefit of doing prefix matching, that is to reduce the amount of advertisement messages. And the last video here is actually to showcase the benefit of internet routing, because one can actually move some of the subnets from one ISP to another, and the internet routing, as we aggregate the prefix, will still work. It's just that for some entries it's not exactly aggregatable, but it will still work.
So the slide here is actually introducing a very interesting scenario. Okay, organization 1 originally here is moved down here to a different ISP. So that prefix advertisement will travel down this way, and ISPRS will try to aggregate it with the original IP address block. Well, ISPRS will find that unfortunately the two of them are not aggregatable. In this case, two separate advertisements will go on out into the internet. The forwarding table here will contain two entries. One is starting with 199 and one starts 200 dot something 18.0 and 23 bits. This one is 16 bits. And of course, this entry here, okay, will arrive also at the router here at the internet, on the internet. And therefore you have 200 dot something, 16 and 20 here. So this entry is gonna take the packet out this interface. These two entries is gonna take packet out here. So if there is a packet coming in that is supposed to go to organization 0, it's gonna match the first entry, isn't it? It's not gonna match the entry number 3 because hey, this address space and this address space, they are actually disjoint. Okay, so not gonna match this guy here. So packet going for destination organization 0 is gonna go down and travel and down to organization 0. So setting up the forwarding table this way, not a problem. Similarly for organization 2 and 3 and all the way to 7. Okay, as long as the destination IP address is matching this, it's gonna come down this way. Yeah, I know you're thinking, hey, what if the packet is going for organization 1? You're right, it's gonna match the first entry. Ooh, a bit worrisome, yes. But if you look down the table, right? Hey, it's gonna also match entry number 3. Now, if we call back in section 4.2, what did we say? We're actually not just doing prefix matching, we are doing what? Longest prefix match. So which one is the longer prefix? 20 versus 23. So packet carrying destination for organization 1's machine is going to come down this way here and eventually reaching organization 1. So we're okay, right? So the overhead of sending the advertisements is still very low. Now slightly higher here if it's not exactly aggregatable, but forwarding is going to be fine. And we allow what? Organizations moving from one ISP to another ISP without changing the physical IP addresses. Okay? Therefore, all these servers are running here. They can stay using the same IP address without needing to change the name to IP address mapping. Now, we get the block of IP addresses from our ISP, but next question to ask. How does the ISP get its own block of IP addresses? So it's like saying, hey, the system admin asks the higher level system admin, but higher level system admin asks the even higher level system admin, right? And this goes on. Who's the highest level system admin? Where's the end? Yeah, this organization is the end. So ICANN here is the highest level system admin. This is a non-profit organization overlooking, okay, the allocation of the IP addresses, the allocations of the domain names, and managing also the domain name servers. So very important organization. We normally don't know. Okay, only the people who knows about the internet knows a little bit about ICANN.
All right, so IP addresses, distribution of IP addresses, and aggregation of IP addresses. All right, the next two topics are called NAT and IPv6. These are related in a way that both of these two schemes are to address the IP shortage problem. Because in IPv4, as you heard, the IP address space is only 32 bits long. Nowadays, many of us might have several interfaces around us already. So that 32-bit address space is not going to be enough. Okay. So the first solution to address the shortage problem is called NAT, Network Address Translation. In this video, the first part you'll hear Polly explaining there's an IP address shortage problem, so we need NAT. And then you will hear the basic idea of NAT and the benefits of using NAT. It's not just that you get multiple addresses easily, but also additional benefits.
NAT, the Network Address Translation Service. This is one of the most used protocols on the internet these days. It's here to address a very serious problem. We're running out of IP address space. Yeah, 2 to the power of 32 sounds like a high number, but we do have a lot more hosts, a lot more router with network interfaces requiring these IP addresses. Therefore, IP addresses is a scarce resource on the internet. To get one, you pay quite a bit of money. This is also why, okay, if this is home network here behind the local network, your deal with the ISP is often this: you pay a specific amount of money monthly, you get a certain downlink bandwidth, certain uplink bandwidth, and a certain number of IP addresses. Usually you get one static IP address or 4 dynamic ones. Okay? If you pay more, maybe 8 dynamic ones. But essentially, the more IP addresses you need being allocated from the ISP, the more money you pay. So it's not like every family can afford paying that much. So to try to save money, this is what we often do at home. Okay? We just, subscribe for one IP address. And then we create a home network, okay, using some fake IP addresses that we make up, and subnet address that we make up. So instead of asking the ISP, okay, asking the system admin for a block of IP addresses, we can afford it. We use fake, okay, block of IP addresses. So we call this local network or home network. Each of the interface is assigned an IP address on the fake subnet. Okay, so these are then fake IP addresses. Now, as long as we are sending data within ourselves, should be fine. But if we want to send data out, wow, we need to be careful. And that's when we need a NAT server here at the home gateway. So NAT is sitting right here. So all packets that's leaving the local network needs to be using the real IP address, the IP address assigned by the ISP. Otherwise, it's going to be dropped, okay, at the ISP. So now if this guy has a connection to go out, and this guy has a connection to go out, and this guy has a connection to go out, each of these connections to not collide to each other will be assigned a new port number as well here, okay, a different source port number. Source IP address changed to the global IP, the real IP, and the port number changed to a different number so that they don't collide to each other. So that is the general idea of NAT. We'll describe the detailed mechanism slightly later. What's nice about NAT is this: we don't need to ask the ISP for a block of IP addresses, which is very expensive. One is enough, save us lots of money. There are 3 more benefits, in fact, using NAT. One is this: if we want to change the IP address in the local network, we just change it. It's not like, we're changing the IP addresses of the gateway there, which is a global ISP, which is assigned by the ISP. Then we need to inform the ISP we're changing it to somewhere else. Otherwise, traffic is not going to flow through. Okay? But if we're just changing the local machine, then there's no need of informing the ISP. Nice, convenient, so save us time. Third benefit, well, if the ISP is not providing good enough service, we can actually switch to different ISP. And the IP addresses we have on the local machines, we don't have to reconfigure them. We just stay using the same fake subnet address, fake IP addresses. The last benefit is slightly unexpected to many of you. Okay? Those devices inside the local network, those 10.0.0.1, 10.0.0.2, those IP addresses are fake ones. Packets originated from outside, from the internet, carrying destination 10.0.0.1 is not going to flow through the internet and reaching the gateway and therefore coming back to the host. Because the IP address of the gateway is what? 138 something. That's the real IP address. That is also what people call the global IP address. And that fake address there is the virtual address, the subnet address. Okay? So subnet or virtual address or fake IP addresses are not addressable. By not addressable is what I meant is packets coming from originated from outside just have no way of reaching. Okay. So they are therefore not visible from the internet, not visible from hackers in the internet. So it's a security plus, okay, unexpectedly.
Okay, so sorry, my stream deck is a little bit slow today. You know what, guys? There's another pop-up quiz on the live chat. So I ask, based on what you heard till now, do you like NAT? Do you like NAT? Do you see that if you subscribe for home access, or at work you don't pay, but for home access, if you need more IP address, real IP addresses, it's gonna cost you, right? So for home access, it's very often that you get a real IP address, but you connect a whole bunch of devices, a bunch of network interfaces to it by using NAT. Whether you are aware of it or not, you're using it probably more than you thought you do. And so, question here, do you like NAT? Just tell me by instinct, right? And we're gonna move on to talk about NAT. The next video explains the exact mechanism of NAT. Okay, so this video is important. I'm pretty sure that there'll be a problem set in the exam that challenge you about the mechanism of NAT.
NAT's mechanism is quite straightforward. Only 3 steps, 1, 2, and 3. Step number 1, you heard about it a bit already. So this is to handle when packet is going out from the local NAT to the world. We'll have to replace the fake IP address with the real one. We'll also replace the source port number with the new port number. Okay, so the source IP address, the source port number, these 2 fields are replaced with these 2 values. And this pair, so 1, 2, 3, 4, okay, are also tracked, okay, being remembered in NAT's translation table. So the source IP and the source port number, as well as the translated source IP, source port number, will be maintained as a pair in the translation table. So when the remote host receiving this packet and sends back a response, in the destination IP address, it's going to be the real IP address, and it's going to be the new port number. So that packet's coming into the local NAT. The NAT box there is going to look up the table and find the pair, right? So it's matching this IP address and matching this new port number, and therefore translate the IP address back to the corresponding port source IP address, and translate the port number to the corresponding original source port number. And therefore, you see the destination fields is going to be replaced by the original IP and the original port number. And that packet then will travel the local network and reaching the destination. Let's use some animation to illustrate, it'll be easier to understand. So the local NAT here, using a fake subnet address. So this machine here, 10.0.0.1, is sending a packet to a web server, okay, outside of the local network, okay, inside the internet. The packet is going to look like this. Source IP being the fake IP. Source port number being the port the web browser is sitting on. Destination IP, the server's IP. Port number, the web server's port number. So that packet is going to reach the NAT box in the middle, and this is going to be replaced. This is going to be replaced. So 10.0.0.1 is going to be replaced by the real IP. And the 3345 port number is going to be replaced by a new port number generated by the NAT box here. Step 2, the NAT router there is going to add an entry into the translation table so that we know this old IP, this old port number is now being changed to this new IP and this new port number. When this packet reaches the web server sends back a response. Destination address will be the source of the request. Okay. So destination port, the source port number of the request. Now this packet will come back to the NAT box in the middle, and one more translation is going to be done. So this time, the process exactly is this. Let's look at the destination port number, and then go to the table. Look up the entry in the table such that the port number in the WAN part matches the destination port number. Now, destination IP address is definitely going to match the WAN side of IP address, because the WAN side IP address is going to be just 138.76.29.7. So this unique new port number is the key. So destination port number, you look up this value in the translation table. Identify the entry, and then replace the destination IP address with the LAN side address. Okay, port number also with the LAN side port number. And that's why we see destination IP address, now the fake IP. Port number, now the original browser's port number. That's how NAT works.
All right, so that was NAT. The last video, I asking pop-up quiz number 2 whether you like using NAT. And many of you say, sure, sure. I mean, I couldn't think of any issues until Pooh started saying that maybe there's going to be some delay, right? Through going through the netbox because there's a translation table that needs to be established, and the IP addresses might need to be translated back and forth. So a little bit of delay. Yeah, that's potentially one of the disadvantages. So next video here is to tell you a little bit more about the issues, how people complain about using NAT.
Last are the drawbacks of NAT. Point number one, poor number, pretty short, 16 bits only. That is also saying we could have only up to 60,000 simultaneous connections. If the local network there is for home use, this is plenty. But if the local network there is for enterprise use, if a company is there trying to save money and subscribing to only one real IP address, having lots of employees, lots of machines inside, chances high the packets going for one flow might be mistaken, okay, with the other flows. Point number two, yeah, NAT is controversial. In the previous slides, you might see the authors of the textbook referring to these NAT devices as NAT routers. But routers are what? These devices in the core of the internet. Now, routers implement only 3 layers of protocol: physical, link layer, and network layer. So routers are also called the layer 3 protocols. Now, layer 3 protocol is supposedly only accessing layer 3 packet header. Layer 2 protocol accessing layer 2 packet header. NAT, if you think about the mechanism again, it's what? Replacing the IP address fields in the packet header. It's also replacing port number, okay, the port number fields in the packet header. IP address, yeah, that is a field in the, yeah, I know, layer 3 packet header. We learned about the IP packet format already. But port number, if you recall, in chapter 3, the transport layer, port numbers are there to differentiate different processes running on the host. It's actually a layer 4 notion. It's in the transport layer header, in the layer 4 header. So NAT as a router should not be doing that. So those who are against NAT boxes to address the network shortage, IP address shortage problem, okay, argue that we should probably, improve IPv4 such that we have more bits for the IP address field. So IPv6 is the next generation. It's using 128 bits for the IP address, much longer. We'll talk about this later. Point number 3, NetBox. Yeah, hosts sitting behind NetBox cannot be reached from a machine from outside. So that was actually presented as a benefit, a security benefit earlier, right? Hackers cannot be sending packets to 10.0.0.1 because that packet is just not going to go anywhere. Okay, not even reaching the NetBox in the middle, the IP address being 138 something something. Right? Only packets with the destination address 138 something something will be able to reach NetBox. Okay? And NetBox there, it will also not know, right, what port number, what local IP address to convert back to reach 10.0.0.1. So yeah, it's actually hard to reach local hosts from outside. So if packets are originated from outside, that's not going to work. Packets originated from inside, however, works. Now we know, right? So from 10.0.0.1, me, the box tracks the local IP address. Okay, keep it in a table. That packet gets translated using global IP, using real IP, goes out. Packet will come back to the router, and the NetBox look up the table and then translate back. So originated from inside, no problem. But data originated from outside, big problem. And this is a serious problem for these designers, P2P protocol designers. In P2P protocol, a lot of time we try to establish connections between one user's host to another user's host. You and me being hosts, we are, chances high, sitting behind the NetBox, sitting behind the net router. So we'll have trouble calling directly to each other, setting connection directly to each other. If you recall in Skype's protocol design, making a call, the designer of Skype actually take extra step. Okay? Bob and Alice will need to call a relay peer, and the relay peer will exchange packets for each other, okay, for these two peers, for Alice and Bob. So application layer designer now need to worry, okay, in case layer 3 or layer 4 protocol is going to break. Okay, unexpected might happen. So one layer's protocol designer needs to worry about another layer's how it's designed, how it works. That's breaking the end-to-end argument. So by this here, okay, what I'm saying is this: the reference protocol stack there, okay, application, transport, network layer. So we say nice about building the network protocols and separate them by layers so that it's modular. Designer in one layer does not need to care about what's inside another layer. Exactly the same thing we are arguing here. Application layer protocol needs to worry about another layer's protocol, how it works. So that breaks the modularity there we have in the original reference stack. And that is what end-to-end argument is referring to.
All right, so that's NAT. We talk about the benefits of using it. We also talk about the issues using it. Okay, and the last one is then you will have trouble having the P2P services running. So essentially, it's hard to set up a server if you are behind NAT, because that server cannot be directly accessed from the machines outside, right? Because so far what you heard from NAT is that, hey, the machines inside needs to establish an entry in the NAT translation table before, right, the outside traffic can come back in. So that's a major technical issue there. Yeah, generally conserving IP is great, but when doing some large things like bigger IoTs, okay, it gets complicated, especially if you want to control the IoT devices at home. Yeah, so guys, I'm still not quite sure, right, whether we do NAT or IPv6 or together, right? Louis was saying that, hey, even if we move to IPv6, it will still be nice to have NAT, right? It's actually, it's perfectly fine. We all move to IPv6, and on top of that, we use NAT. Just in case that we now have a lot of these IoT devices, maybe IPv6 address space is no longer sufficient. So let's keep thinking. A lot of times, you are never really sure something is good or bad. So let's do a little bit more debate, but within your team. So quiz 37 is this, asking you, first of all, would you prefer, so this is, quiz 37. Would you prefer paying for multiple IP addresses or using NAT at home for home access? Okay, and why? Q2 asks, would you prefer using NAT or go straight to IPv6 where the address space is much bigger? And why? Okay, so the first one may be a little bit economical. The second one may be a little bit philosophical. Okay, guys, let's go to the Discord space. W12 quiz 37. For this quiz, I'm asking you from your experience. So let's give it 3 minutes. All right, let's start counting time. All right, good. So I see you guys' opinions are popping up. So Team 6 is the first to say something. Yeah, for Q1, indeed, right? The idea is more economical. It seems that using NAT will be cheaper, right, to subscribe to multiple real IPv4 addresses. Given now that the IPv4 addresses are scarcer and scarcer these days. But for the long run, Team 6 prefers IPv6. And that is in addition to the address space shortage problem that they consider additional features that's building in IPv6, but not that solid yet in IPv4. Okay, so nice. So IPv6 addresses multiple issues that we are suffering from in IPv4 in a way. Good point. And Team 1 here says, using NAT because it's cheaper than getting more real IP addresses. And there are just so many IP addresses we need these days at home, don't we? So in terms of costs, you go with NAT. And in the long run, using IPv6, I guess. Because then you don't have these issues that one needs to translate. There's a bit of delay, as I think one of the students mentioned earlier. Yeah, Gao Pu's point is very unique, right? It's not one of the disadvantages that is actually discussed in the textbook. So going through the netbox, indeed, there's a little bit of delay added. And Team 20 prefer NAT because saves money, but generally prefers IPv6 because then you have more IP addresses. And there's no translation ongoing there all the time. And maybe in the longer term future with IPv6, then in case it's necessary, right, you can still use NAT on top of IPv6. And Team 15, preferring NAT. It's cheaper. Long term, Team 15, very nice. Stick to their own opinions. They will prefer NAT because it's easier to use with the existing network, while IPv6 is still not fully adopted. Okay. Team 15, James, very good point, because the next topic is to talk about IPv6, and one of the issues is exactly the adoption rate. All right, good. NAT and IPv6. I see that the majority opinion is NAT for economical reason, and if possible, philosophically, IPv6 will be longer term solution. And with IPv6 on top of that, we can still use NAT. It's not like we cannot use NAT on top of IPv6. Yeah. So long term, you want IPv6 and NAT in a way. Good. So I think the mass majority is converging. And I love Team 15's answer there, saying that, hey, it's not like everywhere in the world runs IPv6 yet. Good. And you know what? That takes us to the next topic. Okay. And so a really nice connection, IPv6. So the first video is just to tell that we do have this IP scarcity issue, and the IPv6 address space is much bigger, 128 bits.
Last topic in 4.3, the IPv6. This is also the protocol some of these network engineers thought more legit, addressing the IP address shortage problem, instead of using these controversial netboxes. And that is why we actually upgrade from version 4 to version 6. The approach is very straightforward, expanding the 32-bit IP address space to 128 bits long. So the main goal of having IPv6 is exactly this. There are two secondary goals. First is to speed up the processing or forwarding of the packets as they come into a router. So in the data plane, packets coming in really, really fast. If we could reduce the forwarding time, processing time, we make the transmission process as efficient as possible. So you'll see in IPv6, the header is also changed to try to reduce the forwarding time, the processing time. The secondary purpose, this. We want to add something so that we could label the packets, so we could separate a group of packets from other, and make them flows, different flows. Now, with the different flows of these packets, we could then assign priority to a specific flow versus lower priority for other flows. Therefore, we could establish a more flexible levels of quality of service for these different flows. You see also header fields there to support labeling of flows, setting priority of the flows.
So you see that in addition to expanding the address space in IPv6, there are a couple more ambitious goals, right? Speed up forwarding of the packets and to provide different levels of quality of service. Now, next video is important. It's long, 7.5 minutes. In the first part, you will see the IPv6 address format. In the second part, just like when we talk about IPv4, there's IPv4 address format, there's also the IPv4 packet format. So here, in the second part of the video, we'll see the IPv6 packet format. Two very interesting features of IPv6 packet format, particularly the header part, is this. The size of the header is actually larger than IPv4, but the number of fields are fewer. And so the IPv6 header, bigger but more compact.
The IPv6 packet format. The header part of it is fixed size and 40 bytes long. Now recall version 4. Is it fixed size or variable size? It's actually variable size because of the option fields there. So that field, in case we have more options, then it's going to go longer. No fields, 0. And therefore, IPv4 header size is 20 bytes minimum and could potentially be more. Now you probably recall, right? When we were talking about the IP header size, 20 bytes, we also mentioned the TCP header, 20 more bytes. Together, 40 bytes, just to store the control information. If we're sending a real message that's 10 bytes long, the entire packet will be this long, while only 10 of them is effectively sending data. This is very low utilization. So yeah, Poly kind of promised you that in the next version of IP, we're going to reduce the size of the header. But you see here, is 40 longer or 20? Yeah. 46 in fact has a longer header. But this is necessary, and this is as small, as short as possible already. Allow me to explain. In the IP packet header, there are two fields called the source IP and the destination IP. In version 4, the IP address space is only 4 bytes long. Now, to store source and destination IP, you only need 8 bytes. But in version 6, the main goal is to expand the IP address space So unavoidably, we have very long IP address, and two of them, one for source IPs, another one for the destination IP, together 32 bytes. If you look at this, version 6 header 40 bytes, so we have only 8 bytes for the additional fields. While in version 4, 20 bytes long, we have 12 bytes for the additional fields. So the designer of IPv6, you see, try very hard to reduce these other unnecessary part of the header, removing them away, removing these fields away from the header. Okay. So 40 here, longer indeed, but it is actually after we try very hard making the header part as compact as possible, as small as possible. In fact, the second feature of the version 4 header is this. To recall, in the fragmentation and reassembly function of IPv6, we have these 3 fields in a row: ID, fragmentation flag, and offset. This row of extra header fields remove entirely, okay, and this is done by disabling the fragmentation and reassembly function in version 4. So in IPv6, no longer allowing fragmentation. And this is why we see the version 4 header, although longer, it looks really clean and compact. Okay. First, the source address. Second, destination address. And the rest is only just 6 more. 1, 2, 3, 4, 5, 6. First, here is the payload length. If you recall in version 4, we do have what? The header length and the entire packet length. Because the header size can vary. And the packet size, because the data size can also be different, so we need 2 lengths. Here now, having a fixed packet header size, we need just the payload part, okay, the payload length to indicate the size of the data down here. Hop limit, this is just the TTL field, okay, just like in IPv4. Next header, it looks odd, we've never seen this before, but this is really the upper layer field in version 4. So what it does is, once we extract the payload, we actually forward the payload to what's indicated by this pointer here. And so further processing will be done using this handler on the payload. The version field, we also have this in version 4. So the only difference is that this value will always be 6 in version 6. Priority and flow label, these two are new. So flow label here is to allowing us to group a specific set of packets together. Okay, so coming from one application, coming from one service, they could be carrying flow ID 1, and other packets from other services, flow ID 2. So we could identify packets for one flow, okay, and packets for yet another flow. So we could separate these packets traveling the internet. As a result, we could then provide different priorities to different flows. So some flows will go earlier than the others. Therefore, we provide flexible levels of these QoS. Now, there are some more fields we remove, okay, not just the fragmentation fields. The header checksum in IPv4 header, that is removed because to calculate checksum takes time. To check the checksum takes also time. So let's try to reduce the forwarding processing time as much as we can. So let's remove the checksum part. And take the risk of some bits in the header being flipped. We might have some, we might run into some errors, but chance is very low. Okay. We way higher here, way more here, trying to make sure the forwarding part is fast. And we move the option part down to the payload so that when we grab the payload and give it to the handler is going to look at the first few lines in the payload, and those will contain the options. Okay. There's one more thing. ICMP version 6. What is ICMP? You need to think back. In one of the earlier overview slides, I was talking about the functions and protocols implemented in the network layer. Right? In the data plane, we have forwarding. In the control plane, we have routing and management. ICMP is one of these protocols implementing the management function. Okay. So we also extend the version 4 ICMP to version 6. Okay. And the reason we need the version 6 ICMP is so that we could send a special message, packet too big. Okay. allow me to elaborate. Now we don't have fragmentation and reassembly, but the fact that some of the links on the internet allows smaller MTU is still there. So what if we have big datagram coming to a router and the next link is saying MTU smaller, but we cannot fragment this datagram anymore? What should the router do? What can the router do? Okay, so the mechanism in version 6 is to send a special message, an ICMP version 6 message, back to the data source saying packet too big and the better packet size is below this MTU value. Okay, so there's additional message being defined in ICMP version 6, allowing the routers to manage themselves, deciding what is the best datagram size. And we'll just ignore this part. Multicast, we'll just not talk about it at all. Okay, it's a can of worms. So this is IPv6 packet format.
All right. Okay, so that's the idea of IPv6. You see that it's compact. But still, the header size is bigger. The next two topics are about how we move from IPv4 to IPv6. Okay, and we use this technique called tunneling because there's no way we ask all the routers to change overnight from version 4 to version 6. And by the way, guys, let me borrow 5 minutes time today so that we can conclude IPv6. And here's tunneling.
So this topic is a little bit special, okay? We will be talking about how we move from a IPv4 internet to a IPv6 internet. You see, there's no way we turn down all the routers in the world and upgrade to version 6 simultaneously and turn them back on and hope that they will just work. No way. Okay. It's really, really risky. And hey, we are all living in different time zones. What do you mean by having a flat day? And not to mention that turning the entire net down for an entire day, okay, and wait until all the debugging and upgrading is done. Well, yeah, some part of the world might panic. So how will the network operate with part of the internet running IPv4 and some other parts running IPv6? So transition from IPv4 to IPv6, this is what we meant to talk about. How do we allow the mix of IPv4 router to IPv6 routers? And the technique, okay, let me tell you ahead of time, is called tunneling. Okay, establishing tunnels, okay, between routers, okay, at the edge of the IPv6 network to IPv4 and then back to IPv6. And the technique is working this way. So if there's a packet generated from the IPv6 space, so then the network layer in the machine in the IPv6 space will be generating an IPv6 packet. Okay. Once it hits this border between IPv6 and IPv4, this router standing at the border will be implementing both IPv4 and 6. Okay. So this router will also be doing this. Okay. Take the IPv4 packet generated from the take the IPv6 packet generated in the IPv6 space and encapsulate that into an IPv4 packet. Okay, so this is the IPv4 packet, okay, and this is the original IPv6 packet, okay, generated from the IPv6 space. So that IPv4 packet is encapsulated, so being contained, okay, in this bigger IPv4 packet. All right. So you see here, we'll have packet header fields here, source IP address, destination IP address, and etc., etc. Now, IPv4 packet here, coming from the border of IPv4 and IPv6 connection, is going to travel the IPv4 network fine because the header fields interpretable by the routers in the IPv4 space, and eventually reaching the other end, okay, the other border between IPv6 and IPv4, and that border router there would extract, okay, the IPv6 packet, the blue part here, from the IPv4 packet, and then forward it further on onto the native IPv6 space here. Right? This enables an IPv6 machine talking to an IPv6 machine with the middle part being IPv4. I know, allow me to illustrate. So in the scenario, we have an IPv6 space to the left and another IPv6 space to the right. Let's suppose we have data we want to send from A to N. Okay, both of them, version 6, they should be able to send data to each other all wrong. Now the problem is this. Yeah, an IPv6 packet here will travel through the version 6 space. But as soon as it hits the version 4 space, yeah, these routers, they're old. They don't recognize the version 4 format. They will not be able to handle the packet and forward it down this way. Okay? And that is why we need tunnel. Okay? So what's being done, okay, in the tunnel is this. B being the border router, E being the border router separating the version 4 and version 6 space. It's implementing version 6 for sure, but also version 4 as well. Therefore, B and E both carry IPv6 address as well as IPv4 address. By setting up tunnel, B now actually record E's version 4 IP address. E here records B's version 4 IP address. So essentially the two ends, okay, exchange the IPv4 address. So once that's done, usually this is done offline by the network admins. Once that is done, then let's consider, okay, A here generated the packet, the blue one, and we're forwarding it towards the destination. Right? Once it hits the border router here before the IPv4 space, B, the border router, is going to do this. Encapsulate the blue packet inside a version 4 packet. In the version 4 packet, the source address is going to be B itself. Destination address is going to be the other end of the tunnel. Okay, the other end of the tunnel's IPv4 address. Now, this is an IPv4 packet, source being B, destination being E. Then the IPv4 network is capable of forwarding this packet over, okay, at least to E. So E is going to receive the packet next, and being the border router, and being the other end of the tunnel, E is just going to extract the blue packet out of the red one and forward it down to the rest of the IPv6 space. And this is when F here receives the packet that is supposed to go for F.
All right, so that's tunneling, a way to package or encapsulate another version of packets so that you can send the packet to the other end and then decapsulate. So the last video on IPv6 is the adoption rate. It is still a little bit low. We'll come back. Oh, by the way, I'm showing here. This is Google statistics about IPv6 adoption rate. Until today, the adoption rate is still slightly below 50%. But you see that this is a very, very long-term effort. Okay, so this video explains the adoption rate.
Last slide here is not technical at all. It's to talk about the adoption of version 6. So Google once released this number. 8% of the clients worldwide accessing Google services are IPv6. Ouch, please don't. NIST is a government body. They're tracking all sorts of standards as well as maintaining some statistics. So NIST releases this. 30%, 33% of the US government internet is IPv6. Okay. US government is promoting strongly the move to IPv6. And to make the numbers even more pathetic, this is after 20 years of effort. Okay. Ouch. But why, right? If you think at the application layer, we have new applications rising. Okay, IG, Facebook, Netflix, other video streamings, okay, Zoom, YouTube. Okay, newer services rising. Within each service, the protocol also get upgraded quickly, right? Changing from one version to another version. But unlike application layer changes, network layer changes, it seems very hard to do. It's not like undoable, right? We just need to upgrade the routers, upgrade the clients, reconfigure the routers, reconfigure the clients. Why is it so hard? Why is it so much easier to upgrade one app?
Right. Why is it? It seems just hard to make changes, in particular having the routers to change, right? So here's an real evidence. You see that the end to moving the complexity to the edge makes sense because to make changes in the core is just super hard. This is fact. Until now, there's 50% more routers that we are yet to migrate from version 4 to 6. Good. I know you guys probably don't like this. Just making this simple change, seemingly simple change, right? You just upgrade the code. And it's taking so long. So, hey, I ask a question, right? Why is it hard to make changes? Guys, think about it. It might turn out to be one of the questions in the exam 3. All right, and with that said, guys, we've concluded IP version 4 and IP version 6. Next week, we're going to talk about forwarding, but the modern way of forwarding called SDN, Software Defined Network Forwarding. All right, and with that said, I say goodbye, and I see you next week. Bye. Thank you for letting me borrowing 5 minutes time. Oh, it's now 8 minutes time. Okay, bye. Yeah. You too, James, and all of the entire class. And guys, just hanging there. We're just 3 more weeks of lectures to go. And I guess that towards the end of the semester, things get a little bit harder. So try to take things a little bit easier. Be nice to yourself. Okay, bye, Luis. Thank you, Luis, for the participation. Thank you to all of you. So I love the debates about whether you like a NAD or not. I can tell that it's coming from the bottom of your heart. Okay, good. Go get lunch.